So the last important concept that we want to add here with our initial look at work and energy is power. We use the word power all the time, so we want to be very clear about what we mean when we're talking about power in a physics sense. And in physics, power is the rate at which energy is transferred into or out of a system. So thinking about the power is another way of thinking about how your energy changes in some chunk of time, right? So what's the rate at which your energy changes per unit time? Well, one way we can talk about that is with the average power. And again, the average power is defined to be your change in energy over some chunk of time. So delta E over delta T. Well, again, the way we know how to change energy, so our energy transfer that we know of at the moment is work. So I can think about the average power is nothing more than the work delivered to the system or the work done on the system divided by the time it took for that work to be delivered. Now, if I have a constant force, I know that I can calculate the work done by a constant force as the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the force and displacement vectors. Well, if I plug this into my average power calculation, what I notice is I end up with displacement over time, and this is the average velocity. So the average power, two ways I can sort of calculate it here. One is I can calculate the work done by some force divided by the time it took for the force to do that work. The other thing I can do is calculate the magnitude of the force times the magnitude of the average velocity times the cosine of the angle between those two, which means that the average power is also the dot product of a constant force vector with the average velocity. So both of these are ways that we can calculate the average power. So on average, what was the rate at which energy was transferred into or out of the system? Of course, we might also be more interested in the instantaneous power. The instantaneous power is defined to be the derivative of the energy with respect to time. Now, this again is only a really useful definition if we happen to know the energy is a function of time. Often we don't. So what can we do with this? Well, again, since our tiny little transfer of energy at the moment is really just some tiny amount of work that's done, and the work, that tiny amount of work is defined to be the dot product of the force with some infinitesimal displacement through which that force moves my object, what I'm left with is, again, if I rearrange these terms, I've got my force vector dot product with dr dt, and that's the velocity vector. So the instantaneous power, again, since I often don't know what the energy function is as a function of time, what I'm often going to do to calculate the instantaneous power as it's delivered by some force is going to be, well, I know what the force is at that instant. If I can figure out what the velocity vector is at that instant, then I can take the dot product between those two vectors to calculate the instantaneous power. In this class, again, because mostly we're going to deal in two spaces, and so a geometric dot product can be useful, that's just going to be the magnitude of the force times the magnitude of the velocity times the cosine of the angle between the force and velocity vector. That's going to tell me, right, when I do that calculation, it's going to tell me how much energy is being transferred into or out of the system by this particular force at this particular instant in time.